In this video, we'll discover how to perform a multiple object detections and tracking with the use of YOLO, Tensorflow, and DeepShot. So first of all, I will cover a bit of how to set up a local GPU environment because we are going to use a GPU for the object detections as well as the tracking. However, if you already have this set up nicely, please feel free to skip this part. And then on the other hand, I will also show you how to convert a YOLO models to a TensorFlow format, because later on we will need to use this TensorFlow format YOLO models for object tracking. And then I will briefly introduce the DeepShot for object tracking, and finally demonstrate how we could detect, recognize, and track an objects. After watching these videos, I hope you will be able to develop your own multiple object detections and tracking models for your own problems. So let's see how we can set up a GPU environment. If you want to use the GPU versions of the TensorFlow, you must have a CUDA-enabled GPU. And of course, first of all, you need to check the list in the NVIDIA's website to see if your GPU is on the list. If it is, it means that your computers has a modern GPU that can take advantage of CUDA accelerated applications. So once you identify your GPU in the list, you need to install the latest GPU driver, which can be downloaded from the NVIDIA website as well. And you can manually find the drivers for your GPU. Say for example, I'm using a GeForce 1050 Ti versions and using Windows 10, so I just select them appropriately and then search, download, and install the driver. Once you install the driver, you also need to install the CUDA toolkits. And here I select the version 10 and Windows operating systems because this will fit my TensorFlow versions, which I'm going to use TensorFlow 2.0.0. And so you just need to download the toolkits from NVIDIA's website and install it. In the next step, you need to download the CUDNN files. So you probably need to log in your NVIDIA account. And for the first time user, you need to set up a NVIDIA user account. Inside the website, there are many different CUDNN versions. You need to download the CUDNN according to your CUDA versions and your system. So in my case, I download the CUDNN v.764 for CUDA 10, which I set up in previous slide. So once you download the zip files, you should find 3 folders in the zip files. Now you need to go to the CUDA file directory, open the program files, open the NVIDIA GPU Computing Toolkit, open CUDA, and open the version 10. You should see there are many folders inside the directory, but 3 of them should have exactly the same names as shown in the download zip file. That is bin, include, and lib. What you need to do is to open each of the folders in both zip files and the toolkits and copy the files into your folders one by one accordingly. Now you are all set. In this final setup, you just need to set up the Python package and make sure that the package are compatible with each others in order to avoid any warnings or fatal error. And in my case, I use TensorFlow GPU 2.0.0, in which I find that you better to have a NumPy versions 1.16.4 to avoid some warning signals. Although it is still okay to use it, I still downgrade my NumPy just for avoiding the warning. For the programming exercise, you might also need some others Python package. So I just list out all the package and their versions, just in case you might want to take a look. So this is the first line of my package setup. And this is the second slide of my package setup. And this is the last slide of my package setup. Finally, you can simply type in the 2 lines of code for you to check whether TensorFlow can access your GPU, just to make sure that your GPU environment is set up correctly. If everything is fine, you should see a true result. So great, we are all set now. Now, let's see how we could convert a YOLO models to a TensorFlow format. Because in the programming exercise, we will need to use this TensorFlow format for object detections as well as tracking. There are many GitHub files that you can find the YOLO to TensorFlow converter. Here are the few suggestions that I find them working very well. And my GitHub structures follows the AI guys code. So you can also visit my GitHub to download the convert Python file. It's very simple. Just visiting the website, then click on the code, download the zip file, extract and place to your local computer appropriately. So once you download the convert Python program and set up your folder structure according to my GitHub, you will need to download the YOLO3 file and save it into the rate folders. For example, in our programming exercise, I'm going to use Yolov3, so I just download via the link provided here and save the rate file into the rate folder. Now we are ready to run the Python program file. Because the program provides us a command line interface for interacting with the program. So you just need to open a terminal that can run Python script. In my case, I use PyCharm, so I click on the view and click on the tool windows and open a terminal for running the convert Python program. First of all, we need to use command cd get the file directory where the convert program and folders are stored. And then we just simply type python convert.py for converting a YOLO3 into a TensorFlow format. And then if we are using YOLO3 Tiny, we need to specify 3 things. Firstly, we need to specify the path to rate file. And secondly, we need to specify the path to output file. And thirdly, we need to add a tiny flag. After we execute the convert Python programs, we should see field message confirming that the conversions is successful or not. For example, weight loaded and weight saved. But this is not the best way to check if everything is done correctly. So we should go to the rate files for checking, and there should be 4 newly created files, which include 3 TensorFlow files and 1 checkpoint files. And if that is the case, congratulations, you've successfully converted your weight into TensorFlow format and are ready for applying the network for detections and tracking. In the multiple object tracking problems, in order for us to perform an object checking, there are 2 generic steps that includes detections and associations. First, all the objects are detected in the frame, and these can be single or multiple detections performed by different types of algorithms or performed by different types of convolution neural network. On the other hand, once we have the detections for the frames, a matching process or matching procedures is performed for similar detections with respect to the previous frame. And this will help us to confirm whether the objects in current frame associate with the objects in previous frame. And object detections and recognitions can help us in the first step. And object detections detect the objects in an image. In computer visions, it's very often these processes provide you a bounding box which contains the object's x and y coordinates and the object's width and height. However, it will not give the information regarding what the object is. Therefore, in computer visions, we also have another subject called object recognitions. And these processes tell us what kind of the detected objects are, and very often the recognitions output will be a class label. For the detections and recognitions, YOLO version 3 is used in our exercise. YOLO is a detector applying a single neural network to a full image. The network predicts bounding box and probabilities for different regions of the image, and the bounding box are weighted using predicted probability. It predicts detections across three different scales, and for each bounding box, the class which it might contain is predicted using multiple label classification. For the second generic step, associations, that I just mentioned before, object checking is needed. Object checking is a field within computer vision that involves tracking objects as they move across several video frames. The general aims for object checking is to associate detections across frames by localizing and identifying all objects of interest. An ideal tracker should provide a constant ID for each of the objects within the scenes by keeping track of objects even when the detections are missing or false positive. The multiple object tracking problems is challenging since objects can be occluded or temporarily leave the field of view. The appearance of an object can change within the scenes because of scale, rotations, and illumination variance. In general, object tracking is the task of taking an initial set of object detections, creating a unique ID for each of the initial detections, and then tracking each of the objects as they move around frames in the video, and maintaining the ID assignment. One can simply ask, why can't we use object detections in each frame for the whole videos, and that we can track the objects? However, there are few problems with that. If the image has multiple objects, then we have no ways of connecting the objects in the current frames to the previous frames. If the objects you were checking goes out of the camera view for a few frames, and another one appears, we have no ways of knowing if it is the same object. So essentially, during detections, we work with one image at a time, and we have no ideas about the motions and the past movement of the object. So we can check the objects in a video by simply detecting object in each of the frame. One of the ongoing tracking frameworks is simple online and real-time tracking, SHOT, which attempts to overcome the challenge that I just mentioned. It uses Kalman filterings and Hungarian methods to handle motion predictions and data associations respectively. In the short descriptions, the short algorithm keeps track of each object by estimating an object models for every frame. And the object models contains current spatial information about the object positions, scale, and bounding box ratios. The object models also contains motion predictions for the next frames that is estimated using the Kalman filtering. The sort algorithm solves the data associations by calculating the bounding box similarity between objects and detections. And this is done by calculating the bounding box IOU distance. After calculating the IOU distance, the final assignment problem is solved by using the Hungarian methods. And sort is the fast and simple and have high precision and accuracy. But the problem with sort is that the frequent ID switches and cannot handle occlusions very well because sort simply use a simple motion model. And because of that, this motivates an improvement of the sort algorithms and developing deep sort. The full name is sort with deep associations matrix. Deep sort is an extension of the sort algorithms described in the previous slide. It adds in appearance features of an object to strengthen the associations. It utilizes describers for the visual appearance of the detected objects, which are used when matching detected objects from one frame to another to keep track of the identities throughout a video sequence. Therefore, deep sort does not only keep track of motions but also appearance. And because of such an improvement, deep sort very often can reduce the occlusions problems and achieve a higher accuracy. The implementations of multiple object trackings can be divided into three generic steps, and that includes the object detections and recognitions, motion predictions and features generations, and finally the tracking. In the first step, a technique of object detections and recognitions based on CNN is used to calculate the detections. Fast CNN or YOLO are commonly used in this initial detection step on every frame. In the programming exercise, I use YOLO version 3 for illustrations purpose. And in the second step, we need to predict the motions and generate appearance features. An estimations model is created before the data associations. This utilizes the states of each track, such as bounding box centers, box height, box width, and etc. And then the Kalman filtering is used to model these states as a dynamic systems and make motion predictions. In addition, in this step, features generations and bounding box describers are also computed using a pre-trained CNN. So all of these informations are then passed into the final step for tracking. So in the final step, given the predicted status from Kalman filtering using the previous informations and the newly detected box in the current frames, an associations is made for the new detections with all object tracks in the previous frame. For each pair of frames, the cosine features distance, the IOU distance, and the Kalman state distance are calculated for matching updates. And these three steps will continue throughout the video frames and help us identifying and tracking an objects. DeepSort is a very useful tool. Apart from tracking, DeepSort also has been applied for counting the number of people, counting the number of vehicles, and also for creating density maps and heat maps, and also for many other exercises. For example, for countings, very often we will define a gate or a line. If an object is passing through it, we will make a count. And for density map, very often we will create a zone or a grid in such a way that we can count how many objects are going in and going out of a specific areas. And also we can count how many objects are within a specific area currently. So let's go to the programming exercise to see how we could do that. So first thing first, we need to import the libraries for applying the object trackings. So let's import some of the library first. So from ABSL, import flags, and then import, we need to import seats, and then set the flags goes to flags dot flats, and then flats equals to system dot argument. So because YOLO library here is using the command line interface, so we have to uh, import the flat settings for using YOLO's version 3 in TensorFlow later on. So we need these 4 lines just for initializing the flat settings for the YOLO v3. And then we need to import time, import numpy, and import CV, and import the matplotlib dot UI plot as PLT. So here we import time because we are going to calculate the frame per second, and then we need the numpy, we need this CV to OpenCV that is help us to for the visualizing the trackings, and we also need the matplotlib right here is for just for the color map, and then we need to import the TensorFlow, of course, and so, and then from the folder called it, you can check the folder infrastructure, folder structures. You can see that there is a folders named called YOLO v3 EF2. So that is the YOLO version 3 that is in TensorFlow 2 format. So in the models that we are going to import YOLO v3 because we are going to use the YOLO version 3, and then inside the same folder we have the dataset. We are going to import the transform image that is used for resizing our image for the YOLO format. And then we need to also import the YOLO v3 TensorFlow 2 dot use, imports the convert boxes. So that is help us to convert the boxes back to the deep shot formats. So, and then we are going to import the deep shot, import the P processing, which is used for the non-maximum suppressions. And then we need to import the deep shot. From the deep shot, we import the matching, and then matching. Oh, I forget to mention, this deep shot is also under a folder name called deep shot. We just import the program file inside this deep shot models. And for the NN matrix is just for setting up the deep association matrix. And then we need to import the deep shot actions, import detection. Just help us to detect an object. And then we need to import the deep shot dog tracker for providing the track informations. And then we need to, from the tools folders, we need to import the generate actions as GDT. So this is for us to import the features generations encoder. So now we are all set. So first of all, let's initialize the YOLO and load the YOLO class names and as well as the weight. First of all, let's load the um, class name into a list first. I use cdoc script right here for C in open. I'm going to open the Coco file that contains the 80 classes name, and I put it under the data labels folders, and I with FLIes in this coco.names file. And then let's load the create the YOLO model. I'm going to use the YOLO version 3. What I just need to input is just the number of classes. So that is the equals to the length of the classes names. That means that is the length of this class name list. So and then I'm going to load the weight into these models. And I put the weight under the YOLO version 3 Tensorflow format. And that's it for this part. So once we defined the YOLO models and load the rate to the models, now we can initialize the deep sort, including the parameters and also the encoder functions. So first of all, let's define the maximum cosine distance. This is I will use 0.5. This is the threshold for considering whether the objects is the same or not. So if the cosine distance is larger than this 0.5, that means the features is very similar in these two in the objects in the previous frames and also the objects in the current frame. And then we need to assign the NM budget. However, I should say this NM budget is used to form a gallery because for each detections we are going to use a deep network to extract the features vectors, and then this NM budget is used to create a library and then store the features vectors. And by default it is 100, but now I'm setting it to be none. That means we are the NM budget is not enforced right here. And then we need to assign the NMS maximum overlap equals to 0.8. So this is just to avoid if there are too many detections for the same object. So by default, this value is equals to 1. That means we are going to keep all the detections. But however, somehow it might not be a good idea to setting it to be 1 because there might be too many similar detections for the same object, which we don't want to have that. And then we can initialize the default. So the default. So we can now start up our applications and we can then generate the encoder functions as well. So the model file names that we are going to use is the model slash data, that is the mass small 128.pb. So this is a predefined or pre-trained convolution neural network for tracking pedestrians. So I just use these models for illustrating purpose. So, and then we need to create a encoder, which is actually the feature generations. So we have the get dot create box encoder, and then we put in the model files into it, and the batch size is equals to 1. So now the generator or the encoder is ready, and then we need to create a association matrix. So here we use the NN matching dot nearest neighbor distance matrix. And then we are going to use the cosine uh, cosine features or cosine distance functions, and then we just put in back to the um, maximum cosine distance threshold and put in back to the NN budgets right here. So now the deep associations matrix is ready. We can then pass it on to the deep shot tracker. Now we can capture our videos and also assign a file names for saving the output. So here I assign a video by using the video capture doc/data/video/test video .mp4, and this is to capture your videos so you can change your mp4 to whatever videos you want. And then if you replace this path to 0, and then this will use your computer camera. So now we can then record the outputs as an AVI files. So we just need to assign the file format. You writer 4cc and star dot xvid. So this means I'm going to use an AVI file format. And then we need to define the video frame per second and also the video width and video height. So we just get the dv2.cap fps. And then to get this is get the frame per second from the original videos. Because the for the settings, because by default video capture returns a float number, so instead of integer, so I need to use the int functions to get an integer for them. And then for the width and height, we do similar capture. We just cv2.cap and get the frame and get the width for that. And then for the height, similar, we use the similar functions. So that is height. And finally, we are ready to save these outputs. So we have the out as our output, zero writer. So we need to provide a path name to it. So I'm saving back everything back to the video folders. .avi, and then we format to that, then frame per second, and then we pass the width and height to these video writer functions. And so that's it for this for saving the video. And then we move on and we'll create a while loop. So this while loop is used to capture all the frames from these videos. So I'm going to wait the frame one by one with the use of this while loop. So I also add in a if statements that mean at the end of the video, if there is no image, so we are going to print completed and then break the while loop. And then we need to transform a bit of this image capture from each of the video frames uh, in order for us to put it into the YOLO predictions models. So I'm going to use the assign it to the image input for the YOLO predictions. So for we need to convert the color first because the color code in OpenCV is BGR, and however the YOLO or TensorFlow is RGB. So let's convert the color first. Color that should be BGR RGB. Yep. And then we need to expand the dimensions by using the tensor expand dimensions functions. So img in zeros, because the image originally have a 3D array shapes that contains the height, width, and channels. So right now we need to add add one more dimensions to it, that is the batch of the one min that is a batch size. So right now, after using these functions, we will have a 4D arrays as an input to the YOLO predict that contains the batch size, height, width, and depth. So that means we just adding one more dimensions to this original image. And finally, we need to resize the image for the YOLO version 3. The default size for the YOLO version 3 is 416. So we are going to reshape it to 416 here. So we are going to transform the image img in 416. And the image is now ready for the YOLO predictions. So here I start to start the timer, and then we are going to pass the image to the YOLO prediction functions. So the YOLO predictions return us 4 NumPy ND arrays that include the boxes, scores, classes, and also the nums. So by default, there can only be maximum 100 bounding boxes per image that can be detected. So say for example for the boxes right here, it will return say 3D shapes because we only have a maximum 100 bounding boxes per image. So it will return 104 uh, and numpy arrays to us. And these four parameters is the XY center coordinates, width, and height. And then for the scores, it will return at us a 2D shape, and that is the 1 and 100. And then for the detected objects confidence scores in a shorter form. And for the remainings, it will pack it with 0. So, and then it will return us the classes and also a 2D shapes with a 1 and 100. And this is the detected objects classes, and the rest again, it will be packed with 0. And also just a friendly reminder that by default, either is packed with 0 or 0 has another meaning, is a person, is a classes of person. And then for the nums, this is a 1D shaped, that is the 1 only, and that is the total number of detected objects. So because of these four formats are not aligned with the non-maximum suppressions functions later on that we will have, and also aligned with the deep sort functions. So we have to modify it a little bit in order for us to perform the deep sort tracking functions. So first of all, let's get the classes value. So I just need to the first row of the numpy and the arrays, and then we get the extract the class names according to this classes value. So for I in range, we are going to link through the loop through the classes, and then the names dot append. We are going to give the classes name with that is the integer of the corresponding classes. And then we are going to return everything into a numpy array. That is the default format for the non-maximum subtractions and also for the deep sort algorithm. And then we are going to convert the boxes, that is converted boxes equals to use the functions convert box. The image boxes equals to 0. That means we just need to use the first row of that of the boxes. So these functions will help us to remove the 0, the packed zeros, and scale it back according to the original size of the image and convert the boxes into a list. And then based on these converted boxes, we are going to use the encoder to generate the features vector for each of the detected objects. And then we can pass the converted boxes, scores, names, and features into the detection functions, which is actually a class functions that has 4 attributes. So we are going to put the detections under a list. And then inside this list, I'm going to call the detection function with the BB box scores class name feature. That is from inside this for loop. That is the BB box scores class name features. And then in a zip function, inside this zip functions, we are going to have the converted boxes scores. We just need the first row as the entry, and then we have the names, we have the features. So we will have four attributes inside these detections that include the ND arrays for the box informations, which is in a TLWH format. That means that is the top left X, top left Y, width and height format. And then we are going to have the confidence, and that is actually the scores in a ND array as well. And we are going to have the class name in an ND array as well. And then, of course, the features vector that describes the objects contained in this image. And then all these informations will be used to perform non-maximum suppressions on the detection frame to eliminate multiple frames on one target. Just like what I mentioned, detections is a class object. So in order for us to run a non-maximal suppressions, we need to extract the informations from the class object back to a NumPy array. For running a non-maximum suppressions, we need to have a box, we need to have a scores, and also the classes. So we just get back the NumPy array from the class objects for the in the action, that is our class objects, and then do similar we do similar for loop for that, but we get the confidence for the in actions. Confidence is just meaning the scores, and then we get the class name for the in the actions as well. So we will get a index result from the non-maximum suppression, and we are going to pass the boxes, the classes, the NMS maximum overloop, that is 0.x that we set at the very beginning, and we also pass the scores into it. And then this index will tell us which objects that which boxes that should be disregarded. So we are going to pass it back to the detections to remove the redundancy. Now this detections is ready for the deep shot because we just eliminated the multi-frames on one target by using the non-maximum suppressions. So we can simply just call the checker.predict to propagate the track state distributions one time step forward. based on Kalman filtering. And then we need to uh, give the update for the detections that we just have into these trackers, and this will update the Kalman tracker parameters and feature set, and additionally assess the target disappearance and the new target appearance. So that means just two steps will help you to do all these calculations and provide you the result. Now we are ready to visualize the result. First of all, let's create a color map from the matplotlib. So what I'm going to use is the tab 20b, and this is just to generate color maps with 20 tabbed matplotlib objects. So you can consider that the color map is a dictionary which maps numbers to colors, and this is just a built-in color maps functions provided by the matplotlib, and the values at each grid points is a floating numbers between 0 and 1. So and then I'm going to assign a colors from this color map. So just get the three color mapping numbers for I in np.line space. So here I just try to generate a 20 steps colors in a list. So we are going to have a color list that have them that can map with these color maps that generated by the matplotlib. And then we will create a for loop to loop all the results from these tracker. So for track in trackers dot tracks. So if not track dot is confirmed it, or track dot time since update larger than 1, and we will continue to the next loop. So these two statement this is statement is that it means that if Kalman's filtering could not assign a track, and if there is no update in the track, we will skip this track. So just to make sure there is some updates, and also just to make sure that there is an assigned track. So for if everything is fine, then we will just move on to the to get the box from the bounding box from the track to TLBR format. This bounding box format will be used for the CV2 output, for the open CV output. That provide you the minimum x, minimum y, and maximum x and maximum y. And then we need to give a class names from this track. So track dot get classes, get the this is to get the corresponding classes, and then we are going to assign the color based on the color code that we just created outside this for loop. So we are going to give an integer dot track based on the ID, and then divide it by the length of the colors. So this is just to get the remainders for assigning the color code for each of the objects. And then because the color is, as I mentioned before, this is between 0 to 1 uh, value. So we need to times it back to 255 to get back to the um, to convert back to the standard RGB scale in a list. And then we can put everything into a rectangle. That let's put it back to the original image that is the frame of the video. And then we need to provide the start coordinate, and then we also need to provide the ending coordinate. And so the starting coordinates represent the top left corners of the rectangle, and then the ending coordinate represent the bottom right corners of the rectangle. That is just the first two uh, index of this BB box. So this is the first index, and then inside this, I'm going to provide the XY coordinates of the top left corners of the rectangle. And then I'm going to provide it the ending coordinates representing the bottom right corners of the rectangle. So, and then I'm going to give it a color and also the thickness of the box. So after creating this bounding box, we also would like to create a rectangle that is above uh, this, this bounding box to show the length of the class name as well as the class name as well as the track ID. So here we would like to shift a little bit up of this bounding box, and then the starting positions for this will be 0, and then for the ending will be 1. However, um, the ending position should the x-axis for the ending position should have enough size that could contain all the text as well as the track ID. So that means here I add the length with the class name, and then plus the length uh, with the strength of the track ID. So put it in the next sentence. And then for the overall sizing, I would like to give a little bit margin for that. So I just times it by 17. And then here, because I want to fill the color into this rectangle, so I just used -1 right here. And then we can put the axis uh, into this image, or into this inside this rectangle. So we need to provide the x, that is the class name plus plus a hash, and then plus the track ID. This is the class name, and then I need to provide the starting coordinates. So that is somewhere around, should be around in the middle of the box, so around -10. And then I give it the font, default font, and then the font size, and then of course the text color, uh, just 2555 to 555 to 555, and then the thickness of the text is 2. So that's it for this. So it's just this code just means that we are going to put the text uh, somewhere in the middle of these rectangles in a color with a color white color, because we already fill in the colors, so the white color could give us a very nice contrast. So there's a typo here, and also I get this one is an error as well. Yep, typo as well. So we also would like to print out the frame per second. So um, outside should be outside these for loops, because we've already done the tracking right here. So um, so for every frame, just try to print out the frame per second. So we will put it on the image at the top left hand corners. So with 2 voting point and dot format FPS inside it. This is the text, and then put it at the upper left hand corners. The default font style, the default font size, and also put it in a red color with size 2. And then you're going to resize the window for the output into 1024 7x6 768 43 ratio, and then I'm going to show the output and then the image. Remember that at the very beginnings, we also would like to save the output into a file. So we are going to use the outdock write. So we are going to save this image for every frame in the video. And finally, we just to give a wait key to break the while loop, just in case we would like to do that. So break the while loop. So outside the while loop, we just release the video and also release the saving files, and also to destroy all windows. And that's it for this all the codings. Good. Let's see if everything works well. If everything goes well for you, you should have similar results as mine. And here I have around 3 point something frame per second, and people are tracked with class name, person, and also its associated track ID above the bounding box. After running through all the frames in the videos, the file will be saved in the videos folders, and you can see a better and faster video result. Just for your quick reference, the output video should look something like this. So now let's see how we could add the historical trajectory for each of the detected objects. So first of all, we just go to the beginning of the while loop. So here I want to create a bundle length DQ so that the path or the historical data points that can be saved inside this DQ. So here I just from collections imports DQ, and then I just use this point and then create a DQ list with the maximum length to equals to 13 points. That is like a 13 frame for anything that inside the range of uh, 1,000. So here I created a 1,000 list of the queue, and each of the this queue has fixed length with 13 for 30 points. So once a bundle length queue is full, when new items are added, a corresponding number of items are discarded from the opposite ends. So that means the queue or the data points cannot be larger than 30. And then I need to draw the motion path and also visualize it in the image. So inside this for loop, I'm going to add a few lines of code in order for me to do that. So first of all, I need to get the center coordinations of x and y from the um, from for each of the tracked object. So first of all, I need to get the x coordinate center point EB box. So and then this will be divided by 2, and I also need to get the center coordinate for the y coordinate. So I need to get the BB box 1 and BB box bird, and then divide it by 2. So now once we have the center point, I am going to put all the point into under the track ID dot append center. So we have these DQs help us to store all the center point. So now I just need to draw the motion path. So for J in range 1 length, that should be equal to the length of the track. If points track ID j minus 1 is none. All points track dot track ID j is none. So here it means that if the current tracker I if the previous tracker IDs there's no track, and then or if this there's none, so we are going to break this for loop. We are not going to draw anything for this track ID. And then if the current frame is none as well, then we will just continue. We are again, we are not going to draw any motion path for this. Continue. Here I will use a formulas for the thickness that I'm going to put in the for each of the detected objects. So let me type it first. 64 divided by fold j plus 1 and times 2. So what does it mean for this equation is that we are going to keep the closer distance line thinner and keep the farther distance line thicker. So so that means the closer points we will just keep it thinner line, and then for the farther points we are going to visualize it in a thicker line. So I'm going to put everything into a line and visualize with the OpenCV. So I need to give a points DQ for it. So I'm going to give a track ID for the previous point, and then the path, the ending point is the tracker ID, the current frame. This one. And then the color is the color that we just assign, and then thickness is just the thickness. That is this equation. And that's it. Let's see whether it works well. So if it works well, you should be able to see now each of the tracked objects shows its associated historical path. And you can also see that the closer data points show thinner line and the farther data points show thicker line. And this is how it looks like for the saved output videos. So now let's move on to see how we can perform countings. Again, outside the while loop, first of all, we need to create a counter, which is used to count the number of target objects detected. And again, we work everything inside this track for loop. So let's work it at the end of this for loop. Here I need to get the heights and width for the image. So in order for me to um, draw a line appropriately in the image. So let's say we're going to draw a line in the middle of the image. So we are going to give a weighting for this height divided by 6 of this image, and then have the width again should be 1. So we now have a line across the middle of the image, and this line, the color of this line is green, and the thickness is equals to 2. So this should be height, should be height. Here I use 6 is because you can easily tune up and tune down these values to move up and down of the line. And any other values that you can use, it doesn't matter. It's just a conventions. And then I'm going to get the center Y of the for each of the tracked object. That is BB1 plus BB box 3, and then divide everything by 2. So because we just draw a line in the middle of the image, so that we can just track the center Y. So for anything is moving from the bottoms to the top, or anything moving from the top to the bottoms, then we will give a count on it. There are many ways for performing countings. So here I just create a very tiny space in the image. So if anything's passed through this space, it will make a count. And this is a very simple way to do that and work very well for a one-way traffic. But of course, you can create more sophisticated methods for counting. So for me, I just create a if statement. So if the center Y is less than the middle, plus very tiny space, say for example, I create a height divided by 30, and then center Y is larger than the integer minus height divided by 13. So this if statement helps us to create a very tiny space. And then if class name, say for example, we want to track a car or track a truck. So any vehicle. If any vehicle passing through this gate, we will give a count on that. So the counter append will be increased or will be or we will just put the track ID into this count. And then here, I just measure how many counts in this counter. So measure the length of this, and then to get the total count. And then I will output the result with the use of CV to put text image that is total vehicle count plus the strength of the total count. Position should be somewhere around at the top left hand corner as well, and then 0, 1, and then 0, 0, 2, 5, 5, and thickness 2. And then I will output the total counts into the image by using the putText function. And this is the total vehicle count. And what's the strength total count? And then put it somewhere at the top left corner. And style, font scale, and then that is the color, there's the red color, and the thickness of the ends. And I would like to change the video to how to better illustrate this example. So let's see if it works or not. So if everything works well, you should be able to see a line or so-called gate in the middle of the video. And when a curve moves across the line, either from the top to the bottom or from the bottom to the top, the total count will increase accordingly. However, as I mentioned before, this simple method works very well for a one-way traffic. But if there is anything that could reverse in their directions, it might count wrongly. So a more sophisticated method is needed. And this is how it looks like for the final output video. So finally, let's create a zone or a grid in such a way that we can count how many objects are going in and out of a specific area, and also how we can count how many objects within a specific area in the current frame. So before the for loop of the track right here, we make a current count counter here to count how many detected objects or how many tracked objects are within the specific areas at the current frame. And then we need to add just one more line here to visualize the zone. So here, say for example, I try to expand a little bit of the song by 20, and then I just create a song by increasing the height and also reducing the height. So there are two lines right here uh, that we that help us to segment the song, and then we just need to change these parameters to illustrate uh, the song. If anything is within this song, we will give a count. So here I will just give a current count as equals to 1 for counting how many objects are within the song in this frame, in this current frame. And finally, I just need to put another text here. That is the current vehicle count, and then should be change the positions and also change the total counts to current counts, and that's it. And let's run the files to see what we have. So if everything works well, you should be able to see two lines or coded zones in the middle of the videos. And when the curve moves into the zone, either from the top to the bottoms or from the bottoms to the top, the current vehicle counts and the total vehicle counts will increase. And when the car leaves that zone, the current counts will decrease. Similar to countings, there are many ways for creating a density map, heat map, or heat zone. So here, this is just an example or just a very simple methods to count how many objects are in and out of a specific areas and count how many objects are within a specific areas at the current frame. And the final output videos look like this. And that's it for this video. I hope you enjoy and thank you for watching. If you have any questions or suggestions about what we covered in this video, please feel free to ask in the comment section below, and I will do my best to answer. And if you enjoyed this video, you can subscribe my channel, simply like the video, and it's a great support to share this video who you think would be find it useful. And thank you all for watching.